In this video, we'll be dealing about limits. Let's first consider the basic concepts of limits. For this, we consider the equation y is equal to 2x plus 5. If we consider all the points on y equal to 2x plus 5, the line goes like this. And if I consider a particular value of x, say 2, its corresponding value of y will be 9. Let me concentrate on this particular part of the graph, which has 2, 9 as its coordinates on the line. Let me increase the value of x to 2.05. Then the corresponding value of y increases to 9.1. That is, there is an increase of 0.1 on the y value. And if I decrease the value of x to 1.95, then the corresponding value of y will be 8.9, which is there is a decrease of 0.1 in the y value. Therefore, for a particular interval of y value around 9, there exists a similar interval of x values around 2. Let's generalize it. Say I have a value of y as L, whose corresponding x value will be a on the given equation of the line. If I have a small neighborhood of y values, say L minus epsilon and L plus epsilon, and where epsilon is a very small real number, and if I am able to find out another small interval on the x values, say a minus delta to a plus delta, where delta is again another small real value, then we say that the y approaches L as x approaches a. That is, the limit of the y value as x approaches a will be equal to L. You can see the arrow marks, that is, it approaches the L around the value of x is equal to a. This in notation is written like this: limit y as x tends to a is equal to L. Let's continue with the actual definition of limit. If I have a function f of x, and if f of x approaches f of a from both the sides as x approaches a from the both sides of a, then we say that limit of f of x as x approaches a is equal to f of a. And you would have noticed that there are two parts of the limit. One is from the left hand side and the other is from the right hand side. And this part is known as right hand limit and this is known as left hand limit. And the right hand limit is written as limit x tending to a plus of f of x, while the left hand limit is written as limit x tending to a minus of f of x. And we can see that both the right hand limit and the left hand limit approaches f of a. So the right hand limit approaches f of a and the left hand limit also approaches f of a. If this happens, then limit of f of x as x approaches a is equal to f of a. There are some cases where the limit is not possible. For example, if I have a curve like this, and if I consider the value of x at this position, say a, and this part is the left hand limit and this part is the right hand limit. As it is very clear, the function approaches this point on the left hand limit, say L1, and the function approaches this point on the right hand limit. So limit of x tending to a plus, which is the right hand limit of f of x, is equal to L2, and limit of x tending to a minus, which is the left hand limit is of f of x, is equal to L1. And clearly L1 is not equal to L2, which shows that the left hand limit and the right hand limit are not equal. In this case, we say that the limit does not exist. There are more examples. Say for example there is a curve like this, and we consider the point at x is equal to a to be here. Left hand limit is here and the right hand limit is on this side. The x approaches from this side is right hand limit and the x approaching from this side is left hand limit. Let's consider this as, say, L. It is very obvious that there is no right hand limit for this function. Therefore, the right hand limit does not exist. Therefore, this function does not have a limit. Let's generalize now the definition of the limit. This is the left hand limit. If this is equal to the right hand limit, and if both of them are equal to f of a, that is the function defined at the point x is equal to a, then we say that the limit of f of x as x approaches a is equal to f of a. It is also possible that the function need not be defined at the point x is equal to a. The function will look like this. Say that this point is a. There is no f of a. The function has a break at this point. Say this point is L. So the left hand limit, which is this part, actually approaches L. Sorry, left hand limit is this part. The left hand limit approaches L, and the same way the right hand limit also approaches L. But f of a is not equal to L, and it is not defined. In fact, f of a is not defined. Therefore, though the limits are left hand limit and the right hand limit are equal, but it is not equal to f of a. Therefore, the limit as x approaches a of f of x is equal to L, but this L is not equal to f of a. In the previous case, we had a limit of f of x as x approaches a equal to f of a. In this case, we have the limit exists, but the limit is not equal to f of a. Algebra of limits. You can add, subtract, multiply and divide two functions and then apply the limit on that. That is, the first algebra is limit x tending to a of f plus or minus g of x can be split up and written as f of x plus limit plus or minus. If it is plus, it is plus here. If it is minus, it is minus here. Limit x tending to a of g of x. This is for addition and subtraction. The same way it is for multiplication and division as well. You can just split the limits and write it as limit of f of x times limit of g of x. And in particular case, if f of x happens to be a constant, then we have limit of k g of x, that where k is a constant, as x approaches a, will be k, which is the limit of f of x, will be substituted for k times limit of x tending to a of g of x. That is, the k comes out of the limit. The third one is the division of two functions. And if I want to find the limit as x tending to a, I can find the individual limits and divide them. These are the basic algebra of limits. Some very important results which help us to proceed with limits. For example, the first important result is limit as x approaches a of x power n minus a power n over x minus a is equal to n a power n minus 1. Let's prove this. If you just substitute the value of a in this, you'll get something like 0 over 0, which is undefined. Therefore, we need to just cook up and simplify this and get the result. We are not supposed to get 0 over 0 or infinity over infinity as the answer for limits. In those cases, we use some methods and simplify them in order to get a finite number as the result. X power n over a power. X power n minus a power n has an expansion x minus a times x power n minus 1 plus a x power n minus 2 plus a square x power n minus 3 plus etc. a power n minus 1. So this is the formula for x power n minus a power n, which I'm going to use it here. So this will be equal to, I cancel this, and then as long as I don't have x minus a in the denominator, then I am comfortable in applying the limit. The limit gives a 0 in the denominator as long as the x minus a is in the denominator. Now that I have cancelled, I can apply the limit as x is equal to a in this. Once I apply this, then I get a power n minus 1 plus a times a power n minus 2 plus a square times a power n minus 3. I am just substituting the value of x as a. You can see that there are n terms here, and each term is a power n minus 2. This is a power n minus 2, sorry, a power n minus 1. This is a power n minus 1, and a power n minus 1 and a power n minus 1. And there are n terms in this. Therefore, n times a power n minus 1. Let's consider some more important results on limits. This time we will be arriving at some trigonometric results. Let's consider a circle with radius r. This length is now r. And this is also r, and this is, let us say, angle theta. Now if I have to find this will be r sine theta. And if I have to find the area of this triangle, then it will be half times base times height, and the base is r, therefore half r and r sine theta, because the height is r sine theta, therefore which is half r square sine theta. This is the area of this green triangle. Now let me consider the area of this sector. The area of the sector is half r square theta, which is the area of the red sector. Now we can see that this half r square theta is greater than or equal to half r square sine theta. That is, the red sector is bit more than the green triangle. Therefore the areas are compared in this way. Let's consider one more triangle. This one. This is obviously a right angle triangle. Therefore the area of this triangle will be half times r times this side. And what is this side? This side will be r tan theta, because this over this is tan theta. Therefore this is half r square tan theta. Obviously this is the biggest triangle when you compare it to the sector and the other green triangle. Therefore we have half r square theta is greater than or equal to half r square sine theta, and we have half r square tan theta to be the greatest of all the three. Therefore the inequality goes like this. Now let's divide throughout by half r square. Then we have tan theta is greater than or equal to theta greater than or equal to sine theta. Let me divide throughout by sine theta now. Then I have 1 over cos theta is greater than or equal to theta over sine theta is greater than or equal to 1. If I invert the fractions, then I reverse the inequality sign. And if I take the limit as theta tending to 0 on all the cases in this inequality, then I get these things. Now limit as theta tending to 0 of cos theta is cos 0, which is 1. And this we write it as it is because we are going to find the limit of this function sin theta over theta as theta tending to 0. And here it is obvious that this limit lies between 1 and 1, which simply says that the limit is equal to 1. Hence, we obtain the result which says that limit of sin theta over theta as theta tending to 0 is equal to 1, which is a very important result in trigonometry. Here it is very important to note that theta is in radians.